So we mentioned these units in the metric system. Let's take a look at how they fit together. Each type of measurement, as we mentioned, has only one unit in the metric system. So for length, we have the meter, abbreviated with just the little m. For mass, we have the gram, abbreviated with just a small g. And for capacity, we have a liter, abbreviated with either a small or a large L, capital L. Those are our main units. If we want anything smaller or larger, there are certainly things out there that are too small to measure accurately with a meter. They use prefixes to refer to a fraction of that original amount. The prefix deci is 1/10. So a decimeter is 1/10 of a meter. Decigram is 1/10 of a gram. Deciliter is 1/10 of a liter. The prefix centi is 1/100th. That's abbreviated with a small c, so cm is centimeter, 1/100th of a meter. Cg is a centigram, 1/100th of a gram. And of course, Cl is 100th of a liter. Next is milli, which is 1,000th. We have the small m, so mm, millimeter, is 1,000th of a meter. Mg is 1,000th of a gram, a milligram. And ml is 1,000th of a liter, milliliter. Now you can see we went every 10 there. After we hit 1,000, we don't go every 10 anymore. We jump and we go every 1,000. So there's two blank spots here for the 10,000 and 100,000. And we jump up to 1 millionth. And that prefix is micro. Now the mathematical abbreviation for micro, since little m is used for milli, is the Greek letter mu. Looks like that. Looks like a P with an open top, or a U with a long tail on the front. In the medical fields, however, the medical fields were one of the first fields that had to key everything into a computer system. And there is no mu key on the keyboard. So in the medical fields, they adapted MC as the abbreviation for micro. So MCM is a micrometer. MCG is a microgram, or a millionth of a gram. And MCL is a microliter, or a millionth of a liter. But be aware, you may see this abbreviation here, the mu. I mean, if you see mu G, that is a microgram. There are units smaller than micro. I'll mention nano. If you go another 1,000, a nano would be a billionth of a meter, a nanometer, or a billionth of a liter would be a nanoliter. That is about the size of a single atom. So you hear a lot about nanotechnology and nanoscience. What they're talking about when you hear that is they're talking about things really, really, really small, building things from individual atoms instead of from materials. In the medical field, nanoscience has actually impacted the medical field quite a bit with nanomedications. They've actually created little nanostructures for the medications, so time-released medications. So not only do they have medications that will slowly dissolve and slowly release the medication into your system over time, but they've actually got medications that will release different medications over time. You can take a single pill and it'll release one medication first, then a different medication at a different period of time, and actually it'll release different medications at different rates. It's really kind of cool to see the technology they've got there. So nano just means 1 billionth, and for the most part, we're not going to go that small. As we go larger, if we need to measure something larger than our standard units, we have deca. A deca is 10. So since little d is the abbreviation for deci, we use dA for deca. So DAM is a decameter, that's 10 meters. DAG is a decagram, or 10 grams. And DAL is a decaliter, or 10 liters. Next, going up our list, we have Hecto. Hecto is 100, abbreviated with an H. So HG is a hectogram, HM is a hectometer, HL is a hectoliter. That's 100 liters, or 100 meters, or 100 grams. Next up is kilo, which is 1,000. A kilometer is 1,000 meters. Kilogram is 1,000 grams. Kiloliter is 1,000 liters. Now, just like on the other end, once we hit 1,000, we don't go up by tens anymore. We go straight from 1,000 up to 1,000,000. So you're going to skip 2 spots. Skip the 10,000 and the 100,000. One million is mega. Notice I spelt mega with a capital M because the abbreviation for mega is a capital M. Capital M, little m is a megameter, or 1,000,000 meters. Capital MG is a megagram, or 1,000,000 grams. And capital ML is a megaliter, or 1,000,000 liters. Mega is pretty big. 1,000,000 of anything is pretty large. If we look at meters, the circumference of the Earth at the equator is about 25,000 kilometers. So that's only 25 megameters. So on Earth, the megameter is really not useful at all. A megaliter, 1,000,000 liters, that's a lot. 1,000,000 liters is about 270,000 gallons. That's bigger than what we ever need here on Earth for anything. Hopefully you never have to order that much of anything. The only one that's really useful is the megagram, which is 1,000,000 grams, or 1,000,000 is 1,000 times 1,000. It's 1,000 kilograms. Because of the relationship between standard measurement and some of the countries being so ingrained with it, and actually right now the U.S. is the only industrialized country that still uses standard measurement, they developed a unit called the metric ton. The metric ton is 1,000 kilograms. So the megagram has been given the nickname the metric ton. And when we look at our conversions between pounds and kilograms, you'll see it's actually really close to our gross ton in the standard system. So anyway, mega is not horribly useful because it's too large. Micro actually gets used quite a bit. If we look at our units that we have out here, the standard units, of course, get used a lot. Larger units, you almost never hear Deca or Hecto. And for some of you, it may be one of the first times you've heard Hecto in years. Kilo gets used. They developed all these units in between thinking it would be really useful, but it was just too much. They didn't really need all of them. Going the other way, milli is the most common one. And of course, micro gets used for really small things. And the other ones in between don't get used hardly at all. Now, for length, in the United States, centimeters gets used quite a bit because it's the closest thing in the metric system to an inch. It's 2.54 centimeters makes 1 inch. So it's not a really close conversion, but it's the closest there is. And we're so ingrained in the standard system here that we latched onto the centimeter as a unit of measure for the metric system because it's closest to that. But in most other countries, the millimeter is more often used than a centimeter. Now in medicine is one of the few areas where I've ever seen deci used. The deciliter, to be exact. All of your blood tests in medicine are done from deciliters. If you do a cholesterol test and it comes back as a 140, what that is saying is 140 milligrams of cholesterol per deciliter of blood. It's all per deciliter. If a blood glucose test, if it comes back as a 95, that's 95 milligrams of blood glucose per deciliter of blood. So other than that, those are the main units to get used. The other ones kind of get thrown by the wayside. So let's look at our conversions. Now, the way most of us were taught to convert in the metric system, and I'm going to go through it again because I still do it that way most of the time, was just by moving the decimal point. Because you can see every spot on the chart, we're going from, this is the one, 1 unit, 1 meter, or 1 liter, or 1 gram. This is 1/10. Well, if I move one spot on the chart, I'm multiplying or dividing by 10. I go this way, it's 1/10. I go this way, it's 10. When I multiply or divide by 10, what's it do to my number? Yeah, it makes it smaller or bigger by 1 decimal place. Right? Moves the decimal point 1 spot, left or right. And I can actually use this chart to do my conversions. If I have 2.74 grams and I want to know how many milligrams that is, I can look at my chart and say, here's grams right here. Milligrams is 1, 2, 3 spots to the right. So to convert, I have to move my decimal point 1, 2, 3, add a 0, spots to the right. 2,740 milligrams. If I have 410 microliters, and I want to know how much that is in milliliters, well, I can look up here, microliters to milliliters. That's why I left those blank spots in there. It's 1, 2, 3 spots to the left. My decimal point goes from here, 1, 2, 3 spots to the left. 0.410 or 0.410 milliliters. Or if I have 2.9 centimeters, and I need to convert that into meters. From centimeters to meters, I'm moving 1, 2 spots to the left. My decimal point has to move 1, 2, got to add a 0, spots to the left. So 0.029. Simple enough, right? Problem is you don't always have the chart in front of you. So if you remember what the prefix means, you can use that as well. So let's go back to my grams there, 2.74 grams. And I want to convert it into milligrams. Well, we can use that conversion factor like we had before. If I'm going to put grams on bottom here, I know that 1 milligram is how many grams? 1/1000, right? Now, I would probably make it easier on myself and write it as 0.001 instead of 1/1000 as a fraction, just because it's easier for me to think that way. 2.74 times 1, of course the grams cancel out. 2.74 times 1 is 2.74 milligrams over 1 times 0.001 is 0.001. And then I divide that out. 2.74 divided by 0.001 is 2,740. And I have my milligrams on there. If you have a calculator, this isn't so bad, but for a lot of people, if you don't have a calculator, trying to divide by 0.001 is not real pleasant. So you could look at this like this, grams on bottom, milligrams on top. 1 gram is how many milligrams? 1,000. If you can remember that, then grams cancel out. Now what we have on bottom is 1. On top, 2.74 times 1,000 is easier to do. 2,740 milligrams. Now the textbook actually goes one step further. They use powers of 10. The textbook does this. it lists it. This is 10 to the 0 because anything to the power of 0 is 1, right? This is 10 to the negative 1 because it's 1/10. 10 to the negative 2, 10 to the negative 3. Yep. Yes, pretty much. This is 10 to the 1, this is 10 to the 2, 10 to the third for 1,000 or kilo. And what they do is they actually have you use the scientific notation. Actually, our metric prefixes are scientific notation. If I have 43.2 milligrams, now it's not proper scientific notation, but what it really is, that's 43.2 times 10 milli is negative 3, 10 to the negative 3 grams. If I want to convert that into grams, grams is 10 to the 0, right? It's the main unit. My power got larger by 3. Went from negative 3 up to 0. My number has to get smaller by 3 decimal places. Now that one works for me, but for you guys, I can't imagine that not being really, really confusing. If it works for you, that's fine. And that's kind of how the textbook does, is they use those powers of 10 to move the decimal places. Personally, because I'm a math geek, I have that chart memorized, and I move the decimal points. So anyway, those are our metric units and our conversions within our metric units. I had mentioned a couple of things earlier. One is grains. Grains have been absorbed into the metric system. Not a neat absorption. Now for our purposes, 1 gram is 15 grains. This has kind of been widely accepted in medicine, that that is what we use. It's not really true. In reality, 1 gram is actually 15.4324 about grains. Now, we don't like memorizing that number, so we go with 1 gram is about 15 grains. 1 grain, in medical purposes, we say that it contains 60 milligrams. In reality, 1 grain is actually 64.7989 milligrams. Again, not memorizing that number is really not fun. So we just go with 1 grain is 60 milligrams. You will actually see this in some textbooks you look at, and some doctors actually will use 65 instead of 60. I've seen them use 64 as well. 65 makes more sense because it's more exact. Now, here's what always drove me nuts about this, and I mean, you're not going to be tested on this, but how many milligrams in a gram? 1,000, right? 1,000. There should be 1,000. 1 gram should be 1,000 milligrams. But if we use this, let's say I'm going to convert using the grains. If I have 1 gram, put it over 1, and I convert it, 1 gram is 15 grains. So I've canceled out the grams. Then I go, okay, 1 grain is 60 milligrams. So I've canceled out the grains. If I multiply across here, 1 times 15 times 60 is 900. I just converted 1 gram into 900 milligrams. That's not accurate. To me, that's a 10% error. You're going from 1,000 to 900. But they've chosen to round off the grains like that to make it fit in easier. For this class, we are going to use the medical numbers. Now, these don't work out perfectly either. If I did 15 it would be, but For some reason, they have chosen in the medical field to just use 60. Don't know why. If you use the exact numbers that I have over there, it comes out to like 1000.002. I mean, it does, it's just the round off errors. So that does actually come out to 1,000 milligrams in a gram. Like I said, that drives me totally nuts that the medical equivalents, I mean, you'd think they'd want to be even more precise in medical, but they're not. But yes, for this class, I'll shut up now and stop complaining. This is what we're going to use. We're going to use the commonly accepted medical. But the reason I brought up that there are differences, that these are the actual values, is about 6 or 7 years ago, one of the books that they were using in the nursing program for the dosage calculations did use 65 instead of 60. So just be aware that you've got to look to make sure that what you're using. I'm pretty sure right now what they're using does still use just the 60. We talked about minims. 1 milliliter contains about 16 minims. This conversion is also very, very approximate. Remember, we said there's 60 minims in a fluid dram. Now, we're not going to really equate fluid drams to milliliters, but we are going to start talking about our conversions between metric and standard. So let's look at capacity. For capacity, 1 gallon is approximately 3.785 liters. Now there's 4 quarts in a gallon, only 3.785 liters, which implies a liter is slightly larger than a quart. Would have made our lives a lot easier if they'd made a liter equal a quart, wouldn't it? Well, 2 things come into play there. One is they wanted to link the lengths with the capacities. 2 is what we use for a quart isn't the quart that's used everywhere in the world. It is actually really close to the Swiss quart. Metric system, by the way, is developed in Switzerland. It is a Swiss quart is very close to 1 liter. If we're looking at length, by the way, you guys have seen a meter stick. 1 meter is like 39.37 inches. A yard is 36 inches, or a U.S. standard yard is 36 inches. Again, it would have been really nice if they'd have made a meter and a yard the same length. Again, the yard is not standard worldwide. In the British Empire, the yard we use was standard, but Switzerland, again, is where the metric system was developed. 1 meter was actually equal to the Swiss yard. So that's why there's differences there. But anyway, we'll stick to capacities. We have 1 fluid ounce is approximately equal to 30 milliliters. Now I'm going to highlight this one because in your textbook, I have to laugh about this, about 3 pages apart. On 1 page, it says 1 fluid ounce equals 30 milliliters. And about 2 or 3 pages later, it says 1 fluid ounce equals 29.9 milliliters. It is approximate. It is actually just slightly less than 30 milliliters, but 30 is close enough for anything we're going to do. And 1 teaspoon is approximately equal to 5 milliliters. And for our conversions between metric and standard as far as capacity, that's about all we really need. For weight or mass, you know, I said this is one where it's a little fuzzy because we're taking standard weights and we're converting into metric masses. But again, as long as we're on Earth, it's okay. It's not going to change anything. So we're going to convert pounds into kilograms. A kilogram is actually larger than a pound. 1 kilogram contains, we're going to go with 2.2 pounds. It's technically 2.20, 208 or something like that. Or sometimes 2.21 is used. But for our purposes, 2.2 is close enough. And that is a conversion that we use a lot. Occasionally, the teaspoons to milliliters or the fluid ounces to milliliters comes up, but the kilograms to pounds gets used a lot. So let's take a look at some of those conversions. If a patient comes in, has a weight listed as 88 pounds, and our medication is given as so many milligrams per kilogram, we need to convert that patient's weight to kilograms. Now again, as I said, kilograms is a mass, not a weight, but when you hear weight used in medicine, they're usually referring to kilograms. So we're going to take that 88 pounds, we're going to put it over 1, and our conversion factor, I always do what's on bottom first, because what has to go on bottom here? Pounds, because I'm getting rid of pounds. I want it on bottom so it'll cancel out. So then on top, we're changing it to kilograms, so I'm going to put kilograms up there. Now what's my relationship between kilograms and pounds? Yeah, exactly. 1 kilogram equals 2.2 pounds. So once you get the units in there, you just look at the equivalency, and that tells you the numbers. 1 goes with kilograms, 2.2 goes with pounds. So the pounds cancel out. 88 times 1 kilogram is 88 kilograms. 1 times 2.2 is 2.2. So yeah, 88 divided by 2.2 is 40 kilograms. This conversion comes up enough in medicine. It's going to come up enough in our dosage calculations in the next unit that you can take a shortcut. What's going to be the calculation here? Every time we take pounds into kilograms, we're going to end up dividing by 2.2. So if I have a 66-pound patient, rather than doing out the whole conversion factor here, I can just go ahead and divide by 2.2, which is going to give me 30 kilograms. So this whole dimensional analysis thing that I've mentioned here, which is what we did here for unit conversions here, I need to talk about it in a little bit more formally here. Dimensional analysis. Okay, so dimensional analysis is just what we were doing here, where we use the dimensions to tell us where to put the numbers, and then cancel them out just like we would variables within fractions, so that we can do our calculations. And when we do our dosage calculations, one of our methods of doing dosage calculations is going to be dimensional analysis. And the nice thing about dimensional analysis is we don't have to know anything about the substances we're using, and we don't have to memorize formulas. We don't have to distinguish between one type of conversion and another type of conversion, or a flow rate versus a pill or capsulated medicine, because dimensional analysis is just all about where the dimensions are and how things go. For example, if I have milliliters per minute, let's say I have something that is flowing at 8 milliliters per minute. We talked about our ratios and rates last time. When we see a rate like that of milliliters per minute, we need to think this. This is 8 milliliters over 1 minute. In that form, we can calculate with it. If I want to know how many milliliters are going to flow in 20 minutes, I want to know how many milliliters, which means I have to get rid of the minutes, correct? So if I put minutes on top here, it gets rid of the minutes. So 20 minutes. I put it over 1, it doesn't matter. Now when I multiply, the minutes cancel out, I'm left with milliliters. 8 times 20 is 160 milliliters. So in that 20 minutes, 160 milliliters is going to flow. So all I did is I used the dimensions to tell me, am I multiplying by the 20 or dividing by the 20? Well, since I had to put the 20 on top to cancel out the minutes, I'm multiplying by the 20. Now, yeah, you could just do 8 times 20. That's fine. Yeah, that's why I didn't do like miles per hour for driving a car in hours, because everybody knows you just multiply the miles per hour by the time, and it gives you your distance. Yeah. And that's where, you said dividing. Okay, let's say if it's still flowing at 8 milliliters per minute, I now want to know how long to infuse. Let's go 800 milliliters. I want to know a time, right? This does not have time on top. Time's on bottom. So I can't use it like that. I have to have the time on top. So I'm going to start now with my 800 milliliters. I'm just going to put it over 1. This 8 milliliters per minute, that rate can actually be thought of as an equivalency, just like our conversion factors. 1 pound equals 2.2 kilograms. I could either do, most of what we did is 1.1, that's backwards, sorry. 2.2 pounds equals 1 kilogram. I could do that either as what we used is 1 kilogram over 2.2 pounds, or I could do 2.2 pounds over 1 kilogram. That conversion factor can go either way. Same here. I can think of this as saying, okay, 8 milliliters is equal to 1 minute's worth of flow. So then over here, when I want to convert my 800 milliliters and I want to know how long that's going to take, I can put milliliters on bottom and minutes on top. So the 8 goes with the milliliters and the 1 with the minute. So the milliliters cancel out. 800 times 1 minute, 800 minutes. 1 times 8 is 8. 800 divided by 8 is 100 minutes. So at 8 milliliters per minute, to infuse 800 milliliters takes 100 minutes. Now again, some of you could have looked at that and said, hey, 800 milliliters, I'm just going to divide by my flow rate. Say if I'm driving 200 miles at 50 miles an hour, we all know you just take 200 divided by 50, it's going to take 4 hours, right? Same type of thing. So if you know that, you can go ahead and do it. But if you don't see that, you can use the units to tell you how to put the things in there. So if we have a flow rate, let's say it's listed as flowing at 4 milliliters per minute. And we need to know what it is in drops per minute. GTT, again, is the abbreviation for drops. Some textbooks use GTTS. But if we know that for this substance, for this medication that's flowing in, we have a drop rate of 12 drops per milliliter of fluid. Well, then we can take our 4 milliliters per 1 minute. We can create a conversion here. Do we want to get rid of the minutes? No, we still want minutes where they're at. It's the milliliters we want to get rid of. We want to change milliliters into drops. So my conversion here, I want milliliters on bottom, so they'll cancel out, and drops are going to be on top. So the milliliters will cancel out. In this relationship, I think of that as 12 drops to 1 milliliter. So 1 milliliter, 12 drops. 4 times 12 is 48 drops. 1 minute times 1 is just 1 minute. So it's 48 drops over 1 minute, or 48 drops per minute. What do you think? Better than a sharp stick in the eye? Now the textbook gets carried away with the dimensional analysis. It really wants to pound in how this works to you and get you good at working with the units. And it does some things that I consider to be kind of silly. For example, a meter times a meter to the negative 1. Well, if you recall, back when we did our variables, if I had x squared times x to the third, what did I do with those powers? It's x to the fifth. I add the powers, 2 plus 3. So I have x times x to the negative 1. This is a power of 1, right? What's 1 plus negative 1? 0. I'd get x to the 0. What is x to the 0? 1. Yeah. Anything to the power of 0 is 1. So over here, it's the same thing. Meters times meters to the negative 1. Well, that's a power of 1. 1 plus negative 1 is 0. So that's meters to the 0 of just 1. It cancels out. A gram squared, which I have no idea what a gram squared would even be. But divided by a gram. Just like having x squared divided by x, what do we get? Just x, right? Think of this as being x to the 1, 2 minus 1 is 1. So it's x to the 1 or just x. Same here. Gram squared divided by a gram is a gram. So in the textbook, they get a little silly with it. They give you problems like this. A meter times a gram squared over a liter to the negative 1 times a milligram times milligrams over grams times liters. Now you might be looking at that thinking, huh? Yeah, it's kind of, it's taking it to a way extreme. But first thing I do is when I see grams squared is I do this. I cross it off and it's grams times grams. Anything squared is times itself, right? So now it's easier. I can cancel out one of the grams with one of the grams. I can cancel out a milligram with a milligram. So I can cross cancel anything on top that matches up with anything on bottom. Now what I have on top is meters times grams. Meters times grams. On bottom I have liters to the negative 1 times liters. What's that? 1. Because it's to the negative 1 times itself. It's 1. So this ends up being meters times grams is what the units end up being there. Again, a little bit nonsensical, but you get the picture. Or we might have liters times meters to the negative 1 over milligrams squared times meters times milligrams over liters. Now again, it helps me if I cross off the milligrams squared and I just write milligrams times milligrams. Now I can cancel out milligrams on top and bottom. Anything else I can cross cancel? Liters and liters, yep. So now if I multiply on top, meters to the negative 1 times meters is 1. And on bottom I'll have is milligrams, so it's just 1 over milligrams. The book may list that as milligrams to the negative 1 because it's a reciprocal. It's the same thing. Like I said, I'm not really impressed with that effort to... I mean, I understand what the book's doing. It's really trying to ingrain that dimensional analysis into you, but it's a little silly. It's kind of nonsense units. But the practice of canceling out units like that is very good. The problem is if the problem is preset like this, then it takes out half of the effort. Most of the benefit of dimensional analysis, it tells you where to put the numbers. If I am starting out with 17 milliliters, and I need to convert it into, let's say fluid ounces. Need to figure out what that is. Well, I know somewhere I look up and I see 1 fluid ounce equals 30 milliliters. So now I can take, and I can set this up. I can take my 17 milliliters. I'll make it a fraction by putting it over 1. And now I know that the milliliter, because milliliters on top and I need to get rid of them, that tells me milliliters have to go on bottom. Which means this is the equivalence I'm using to convert. That tells me fluid ounces have to go on top. And the relationship is 1 fluid ounce and 30 milliliters. Now the milliliters cancel out. I have 17 fluid ounces over 30, and I divide. Gives me 0.633 fluid ounces. to me, that's the power of dimensional analysis, is by looking at the units, it tells you what numbers to put on top and bottom of the second fraction, not having them already there and then being able to cancel them out and combine them. I'm going to have you do a few of those in the textbook anyway, just so you can practice. The last thing in this unit that we want to talk about, we mentioned it a little bit when we were talking about converting formulas last class, is temperature. For temperature, we tend to go with water as our baseline. So we're looking at, first of all, we'll talk about degrees Fahrenheit. Now I'm not even going to try to spell it out right now. I'm tired and I've been screwing things up. And degrees Celsius is our metric temperature. So if we look at water, our benchmarks seem to be that when water boils and freezes. In our Fahrenheit system, our standard system, what temperature does water freeze at? 32 degrees Fahrenheit. What temperature does water boil at? There we go, 212 degrees. I've been finding in recent years more and more students don't know that one. In the Celsius scale, what temperature does water freeze at? 0 degrees Celsius. What temperature does it boil at? 100 degrees Celsius. Because there's 100 degrees between freezing and boiling, the Celsius scale is sometimes called the centigrade. Centi means 100. Centigrade scale. So anyway, if you look at our Fahrenheit scale, between freezing and boiling, that's 180 degrees. In our Celsius scale, it's only 100 degrees. So that tells us that the size of 1 degree is different from one scale to the other. The problem is 0 degrees Celsius is not equal to 0 degrees Fahrenheit, and the other way around. Every other conversion we've done, 0 has been 0. 0 meters equals 0 inches. 0 kilograms equals 0 pounds. I mean, 0, there's a common 0 point no matter what measurement system or measurement unit you're using. For temperature here, there's not. So that's where we have to use one of those formulas. And we talked about the formulas last week a little bit. If I have the temperature in Fahrenheit and I want to know the temperature in degrees Celsius, I take my degrees Fahrenheit, I subtract 32 from it, and I multiply it by 5/9. So let's say today, what's the high going to be? Around 80 degrees today? So it's 80 degrees Fahrenheit. What's that going to be in degrees Celsius? Well, we put 80 in here for F, minus 32, and now it's just order of operations. 80 minus 32 is 48. 5/9 times 48, 26.67 degrees Celsius. Where this formula comes from, the subtracting 32 is because the starting points are off by 32 degrees. Subtracting 32 takes the Fahrenheit temperature down to 0, to a common 0 point. The 5/9 comes from the 180 and the 100. The ratio of 100 degrees between freezing and thawing to 180 degrees between freezing and thawing, if I reduce that down, both divide by 20, give me 5/9. So it's a 5:9 ratio. Going the other way, if I have the degrees Celsius and I want to convert into degrees Fahrenheit, well, instead of multiplying by 5/9, I'm going the other way. I multiply by 9/5, and then I add the 32 degrees back on. Notice it's the exact opposite process. We talked about solving equations. You build an equation, and then you take it back apart. You do these opposite steps in the opposite order. Well, that's exactly what happened here. Here we took F, we subtracted 32, and then we multiplied by 5/9. Well, the opposite of multiplying by 5/9 is dividing by 5/9, or multiplying by its reciprocal, 9/5. So to go the other way, we did the opposite. We multiplied by 9/5, and then we added the 32 back on. The opposite operation in the opposite order. So if I have a day that is 20 degrees Celsius. What's that going to be in degrees Fahrenheit? Well, 20 degrees 9/5 times 20 is 36. Plus 32, that is a 68 degree Fahrenheit day. Pretty nice day. Okay, pages out of your book for you guys to look at. Page 103, 119, the odd. Page 110, 1 through 41, the odd. Page 114, 1 through 25, the odd. Page 118, 1 through 19, the odds. And finally, page 123, 1 through 21, the odds. This does wrap up Unit 2, which means Unit 2 test will be next Friday. First hour of class, generally I figure about the first hour and 10 or hour and 15 minutes of class. You'll have a little bit more than an hour. As always, you can come in and start early if you want to. I'll make sure the other locations have it early, and there'll be a note that you guys can start early if you need to. Now, the first test, we had a section with no calculator. From here on out, everything we do, you'll be allowed to use your notes, your books, and your calculator on everything. So just so you know.